Yeah, in the last movie, I was discussing how this part here would be functional gauged when the primary datum is referenced at maximum material boundary. Okay, so when we're talking about this last part right here, our primary datum was a surface. Okay, in this particular part, our primary datum is a feature of size, in which case it's this shaft here. Okay, so in this feature control frame, that shaft is referenced at maximum material boundary. Okay, and so our virtual gauge looks something like this, where we have a feature here to pick up the datum C simulator. If this was an actual part, I would have a basic dimension locating this datum C relative to this datum A. But anyways, so datum C simulators right here, it simulates that surface. We got a datum B. Datum B is a surface too. It simulates this one right here. Um, the the shaft here, the cylindrical feature, it pops into this hole here. This hole is made at the MMC of the primary datum. The MMC of the primary datum would be this 500. MMC would be this 503 shaft. That's the MMC, is this 503 shaft. So that fits down there for the 503 shaft. And then these pins here to pick up these 219 holes, those are made to the virtual condition. The maximum hole would be, MMC hole would be 219, and then we would subtract from that the positional tolerance of 8 to get 210. So this is what that feature, a primary datum is referenced at the maximum material boundary, and this is what the functional gauge would look like. And which is interesting because in this case it's, the datum A here is just picked up at MMC. Now what would happen to this same type of part if the primary datum was referenced at regardless of material boundary? Okay, this is a little bit different situation. Okay, we got essentially the same part, except um, we don't have this A is referenced at at maximum material boundary. So okay, this is in line with rule one. We're going to assume that A applies regardless of material boundary, in which case we need to have an expander plug in our functional gauge that will expand to contact this feature regardless of the feature's size, or regardless of the feature's boundary. Okay, so instead of just making a center plug in here, instead of just making a center plug in here at the maximum material boundary, we have to have an expander that finds this datum at regardless of its material boundary. Okay, so it's a lot more complex than coming up with a gauge that just checks at MMC. Okay, on this slide, we're looking at using a simulation of a secondary and tertiary datum references at MMB. Okay, so what we have here is we have a part, we have datum D is a surface here, and then we have these holes that are located on like a bolt circle, and we have a tolerance for these holes. We have a positional tolerance of 24 thousandths at MMC to datum D, which is primary, datum J, which is the secondary, which is this bore in the middle, and then datum K, which is this slot keyway here. Okay, so what we're going to do, because we're referencing everything to MMC, these maximum material boundaries here, J and K and J, are also done to the maximum material boundaries. What is our functional gauge going to look like? Okay, so first of all, what we need to do is we need to pick up a simulator for datum D, which is this surface right here. That'll be our datum D surface. That's this surface right here. And then we have to have a simulator for datum J, which is our bore here. Our bore is at 1.378. That's our maximum material condition of the hole. 1.378 minus the 3,000ths. This is a perpendicularity tolerance and orientation tolerance. So we have a 1.375 virtual condition. So our datum J simulator is a diameter, a fixed diameter of 1.375, which is the virtual condition of the datum J. And then next, we also need to pick up this keyway here too, and it's toleranced at MMC. Okay, you look at it right here, it's tolerance right at MMC, maximum material boundary, MMB. Okay, so what do we do with that? Okay, our slot is 254 thousandths wide with 4,000 some true position, and then we also have this tolerance right here. Okay, so what is it? The 254 is our MMC minus the 4,000ths tolerance. Okay, and then it's also minus this 3,000ths tolerance for this feature right here. And so what this gives us is 400 and 247 virtual condition of the slot. So what we do is we have a simulator that picks up that key slot in there at 247 thousandths. Now once we have that, we're going to put our pins in at the virtual condition, which will be the 312, which is our MMC, minus the 24 thousandths of our tolerance here. So we got the pins in at the 288 thousandths, which is our virtual condition. Okay, so what we've done is we built a simulator over here. The simulator picks up the feature of size, which is the hole here, at its MMC. And then we also have a feature of size here in this keyway, and we're picking that up at its virtual condition. And then we're picking up the holes here and checking their true position at virtual condition. So that's how we do that. So the pins are used to check hole locations, are always sized to the virtual condition if position tolerances include the MMC modifier. Okay, so let's talk about gauging a composite feature control frame. So gauging a composite position tolerance. So the pattern locating gauge simulates all the reference datum features. It constrains the translation and rotation of the pattern location tolerance zone framework relative to its reference datum features. And the pins at the holes true positions relative to the datums, and they're going to be sized at the virtual condition. Now from there, we're also going to have a feature relating gauge, simulates only the reference datum's features in that applicable segment. So this feature relating gauge constrains only rotational of feature relating tolerance zone framework relative to reference datum features. And then the pins at the hole true positions within the tolerance zone framework and also sized to the virtual condition. What does this mean? Okay, so here we have our composite datum, our composite positional tolerance here. We have 32 thousandths at MMC to A, B, and C. We got the simple prismatic part. From the datums and the basic dimensions, we can establish the tolerance zone framework. So here is our gauge for the pattern locating tolerance. Okay, we have a simulator for datum A right there. We have a simulator for datum B right there. We have a simulator for datum C right there. And then our holes, our pins here for our gauge, they are made to the virtual condition of the holes, which would be this 375 MMC minus the 32 thousandths to get us to the 343 virtual condition. Okay, so we check these really essentially just to the upper segment is really what we're doing. And then next we're going to have a separate gauge just for the feature relating tolerances. Okay, now if you notice, it just has a simulator for datum A. See, we only reference datum A in the feature related tolerance zone framework, so we only have a simulator for datum A. And then the holes, the pins to inspect the holes, they're only made to a different virtual condition, which would be the 375, that MMC of the hole, minus the 16 thousandths tolerance at MMC. That gives us a virtual condition of 359. So we make our pins to 359, and we have 3 of them at the proper locations, and we mount it with a simulator that picks up datum A. So to check and gauge a composite position tolerance, we can use 2 functional gauges for that. Let's talk about coaxial holes. This is kind of like a hinge, okay, or something like that. So what we have is we have holes that are all in line with each other, and what we want to do is control them to each other. So typically, like, if you have like a hinge, and then you had to put a hinge pin in there, you would have these holes, and you would have a pattern locating tolerance zone framework, which could have a bigger tolerance on it. But once you locate those holes, man, you need to control them tighter to each other. So we have this. That's where we have this second, feature relating tolerance here. So the patterns can have a large tolerance, and the holes can have different diameters, like we're showing here. Okay, and then we could apply that to all 3 of these coaxial holes. Now, what does that mean? Okay, so if we're looking at our pattern locating tolerance, that's the 16 thousandths at MMC. It establishes this pattern, specified pattern location over here, and it specifies the pattern locating tolerance zone framework for that pattern, and that would be to a virtual condition of 362. Okay, so once we're in that pattern, we have a much tighter feature relating tolerance zone. Okay, so in which case here we have a much tighter, our virtual condition is down to 372, and it fits right through there. So there's our axis of the holes. So once we locate our pattern, we want to hold them tighter. Okay, and just that. So I like to end this movie right here. I got a couple more topics I want to finish in the next movie. Thank you.